This is Fedora 17 running on a fast computer i7 at 3.5 gigahertz. There are many cores, 8 cores plus 8 more hyper-threaded. Now the bottleneck is the first FFT, which runs in a single thread. It uses about 77% of the CPU power. I look at the timing and it says actually 84% for the wideband DSP, that is the first FFT, and then 21% for the baseband filter, giving this window. Other threads have very small load. As you can see, there are glitches. The computer is not quite fast enough, or maybe I have not programmed it well enough to handle a high load like this. Anyway, the purpose of this video is to show the performance of the pcie9842. I have a test oscillator at 10.7 megahertz, and as you can see in the S-meter graph, I have put this calibration number to make it show 0 on the carrier. So now when I move away from the carrier with the mouse wheel, like this, let's see, we had 670.5. 680.5. This is 10 kilohertz away, and here the noise level is, I have to move the graph, it is minus 117, and that is in a bandwidth of 1 kilohertz, which means that the noise floor is 117 plus 30. That is 147 dB in 1 hertz bandwidth. This is very good. The pcie9842 is sampling at 200 megahertz. Linrad cannot handle that, so the interrupt routine or the callback routine from the hardware takes the average of the data points in groups of 8. That means that the samples get better statistics, that means better signal to noise ratio, but that the sampling rate is only 25 megahertz. And that gives a bandwidth of 12.5 megahertz. As you can see, that's where the window stops. If I go, now you can see other things. Here is a spur. It's a resampling spur because at these high sampling rates and with the current hardware and programming in Linrad, I cannot apply appropriate windows to suppress these spurs better. The level is, as you can see here, minus 82 dB. It's not a strong spur. Now if I go to a somewhat larger distance, that was 10.7, so I go to 10 point, let's say, well, I have forgotten. The signal is at 10.6. The signal is at 10.670. So I go 100 kilohertz away, maybe here, 10.5 570. This is 100 kilohertz away. And here the level is minus 120 in 1 kilohertz, means minus 150 dBc per hertz. That is full quality of a modern digital receiver. And if you look, you can see that the noise floor falls off. I can click, let's say, 1 megahertz away. It will be about here. And actually, the difference isn't very big. I have now been running a crystal oscillator. It's this thing, a homemade crystal oscillator. I will now connect instead a conventional signal generator. So I connect away this thing and put it in here. And then you can see what happens on the screen. The signal generator is not bad at all. It's an pcie9842, which is a low noise machine, but compared to modern digital technology, it isn't really very low noise. You can see here 1 megahertz away, the noise is about 14 or maybe 13 dB above what we had from the signal from the crystal oscillator. And if I remove the input totally, that means no input at all, and then back again to the crystal oscillator. You can see here that there is practically no difference. There isn't any phase noise on the sampling clock that adds noise at a distance of 1 megahertz. So it looks like this sampler is perfectly okay as a radio receiver. I have now connected a whip antenna. It goes from DC to 12.5 megahertz. The noise floor at 12.5 megahertz is very close to the noise floor without any signal at all. That means some more gain is needed. So with maybe 10 decibels more gain, the noise floor here would be lifted so that we would overcome the noise of the pcie9842. But in the medium wave range, let's click somewhere in the medium waves and look for a minimum between stations, maybe here. There is no need for more gain. If I continue to tune, trying to find a low level, the noise floor is about 5 to 10 dB above the noise floor of the card. So for optimum reception, I need an amplifier with near zero gain from DC up to, let's say, well, what's here, up to 1.5 megahertz or so. And then with increasing gain here, already here maybe 10 dB and maybe 15 dB at the high end. Linrad is not up to this yet. The first FFT is the bottleneck. It cannot do more than 12.5 megahertz, and when doing 12.5 megahertz, it is a compromise. There is a possibility to use the graphics cards. A modern graphics card can have 3000 CPU units working in parallel. They should be probably at least a factor of 25 faster than this computer, and then it might be possible to run from DC to 50 megahertz with full performance. It will be possible by splitting the workload of the first FFT on more CPU cores to allow a little bit better performance than we see here, but not a big factor, maybe a factor of 4 or something. That would allow a proper window to get rid of the spurs, the resampling spurs I showed before, and also get rid of the glitches that happen now and then due to inadequate CPU speed, or maybe inadequate programming, I don't know. I now switch for AM, that's X, X, F, and accept defaults. This is low run. Defaults are no good. The computer is saturated. I have to go X, P, and set a wider bandwidth here, let's say 3 kilohertz. That makes the FFT size small enough to make it fit into the cache memory of the CPU. That's an important thing. Let's make that 7 instead and have a look. What do we have? Click on something and you see I'm moving the mouse without clicking and it doesn't work properly. Means something is overloaded. The CPU load says 87%, but that's not a safe indication that things work properly. When there isn't time to do something, the computer will get idle rather than working on something that it knows it cannot do in time. X, P, this should be okay. I can reduce that to 2. X, P, make this So you can see here the wideband DSP runs at 99.38%. That's not really a good idea. And I don't know why this happens, but I can set an easier window here. And listen to AM stations. And with the appropriate bandwidth, here something. It's now in the middle of the night, so the medium wave is full of stations. Here is a strong one. Sounds like the other one I just had. And
ook denken, de tijd van Jacobs benauwdheid, dat stuk nog voor ons ligt. Want er staat geschreven dat
and the long wave here, 252, I happen to know is BBC One. So, we have a nice radio, but Linrad is not quite up to processing it yet, but I'm working on it.
Signals are much weaker in daytime. We can see here there is some noise visible. I'm just now on a local MDB. And down here from DC up to maybe 50 kilohertz, there is various kinds of interference. I don't think these are real signals. You can see. Or it could be, I don't know. BBC is at 252 here. It's very difficult to hear it, even though the noise floor is lifted a little bit, so BBC is weak today. Normally can hear it better. And of course, stronger stations are. And 7 megahertz. No broadcasting. Or not much broadcasting. Here is the station at least. The bandwidth is a little bit too big here. Something like this. The amplitude margin here, 22 decibels only, is the same as at night time. It is caused by the DC component. You can see DC goes all the way up to the top of the scale. I have to click here, and you see the DC component is 103 decibels or something. And that is high above where the signal levels were at night. So the card can accept a significant gain in front of it without going into saturation. Now, in Sweden, we don't have medium wave transmitters. In another country or in a location nearer to a transmitter, the performance of the card is needed if one wants the full bandwidth into it. And in many locations it may even be necessary to put a notch filter for the local medium wave transmitter.